Okay, ladies and gentlemen, this is lesson 6.5. So we're going to take all of those strategies that we have for solving quadratic equations. It's completing the square, factoring, and quadratic formula, or graphing. And we're going to talk about when we can use them, and then we're going to use them to solve a couple of different word problems. Now, something you need to know, who can fill in the blank for me on the top of your notebook, page 21? There is...
4.
There's no way.
Infinite.
There is no way to solve a quadratic... No, there is more than one way. There is more than one way to solve a quadratic equation. We saw that right from the beginning of the unit when we were doing smaller, simpler ones, such as this. Okay? There's more than one way to solve this. One way would be to add 9 to both sides and then take the square root of both sides. Okay? The other way would be to say, oh, this is a difference of squares, so I could factor it, x minus 3, x plus 3, and find out that x equals 3 and x equals negative 3, which is exactly what we got here. Just a quick demo to show you there's more than one way to solve a quadratic equation. So let's talk about those ways. Graphing, factoring, completing the square, quadratic formula. We're going to take a couple of notes. When can you use graphing?
When you have to graph it.
When can graphing work? Like going on Desmos and punching it in. Can you do that all the time?
No. Because you won't have intercepts.
Okay. So if it's not solvable, then none of these will allow you to solve it, right? So that's
But
fair.
you could technically do it for everything, because if you get the right answer...
You can graph any parabola, okay? You can graph any quadratic equation. So when can you use graphing? Always.
Always. What do you mean?
You can use it always. Now, it's not always the best, though, because your solution will not always be exact, right? You're just looking at a picture. You're not algebraically finding out exactly what x equals. So the comment there is solutions will not always be exact. Solutions will not always be exact. What does that mean? That means use it only when you need an approximate answer. Okay? The next option that we are talking about is factoring. When can you use factoring, like sum and product? This is, if you need help remembering what this is, you'd use sum and product or factoring out the common factor. Okay? When can you use that? Always?
No. Sometimes
No.
it's non-factor.
Only when it's in
When there's a GCF.
Only
when it's
form.
in standard form. When there's a common factor.
So sometimes, and we're going to say, yeah, so if there was a greatest common factor, that would mean there's only 2 terms, and that would mean c is 0, right? If we're thinking about ax squared plus bx plus c. So you can use when c is 0, or factors are easy to find. So, I mean, that might not sound so easy, but when you get something that's in don't write this, ax squared plus bx plus c, and you can split the middle term using sum and product, and you can factor by grouping, and you end up with 2 binomial factors, or maybe even a third factor out here. Okay? If you can do that easy enough, then use factoring by hand. Okay? Good. Yep.
So if c is 0 and you have to use sum and product, and you have to times a for c to get b, then wouldn't it just be 0?
Okay, great question. So if c is 0, then that means essentially you have something that looks like this, which means you're not going to factor using sum and product. You're going to pull out a common factor.
Oh,
And now you have the solutions x equals 0 and x equals negative 2. Okay? Yep.
Could you maybe do like 2b on the thing to show us?
Not right now, but yes. You can come in at lunch anytime.
Yes, I will
Okay,
do that.
good, here we go.
I always
I'm
come
so
out
done
with
with
first
talking.
try.
The other option is, there is another option, completing the square. Everybody's favorite. That's from lesson 6.1. Okay, when can you use this? You can always use completing the square. No matter how difficult the quadratic looks, you will be able to complete the square because you can always take half of b and square it and find a trinomial that's a perfect square that you can represent as a binomial squared. Okay, so when are we going to use this? When are we going to use this?
When we need to find
easiest.
binomial.
When we have ax squared plus bx plus c, and b is an even number. So you can use it all the time, but that's just when it's easiest. The last one that you have there is quadratic formula.
That's my favorite.
When can you use that one?
Always.
Always.
Because it's so
Okay, it's long and cumbersome, so you don't want to use it for these easy ones. You want to factor first if you can, but if you can't, if it's too hard, or if they're not integer factors, or if they're not integer solutions, then you might want to go to the quadratic formula. If you can't find a sum and product, two numbers that multiply to AC and two numbers that add to B, then you want to use the quadratic formula. Okay, and what's the note on that one? This gives exact solutions. Now we usually round ours when you take the square root under the radical there, when you actually square it. When you square root it, you're taking a rounded number because you're taking a number that has decimals. But you'll hopefully remember that when we get there. Again, don't use this one unless you have to. Okay, there's your 4 methods that we can use. If it's a real hard one, you graph it, quadratic formula. You start with the easier ones, okay? You start trying to factor it. Factoring is
What
easy.
if I know the harder one the best?
And use that one.
Oh.
In example 2, we have a park and a path being paved around the outside of the park. So we have a park, a rectangular park measuring 100 meters by 60 meters. And the first thing I'm going to do while I'm reading through it is just kind of draw what they're telling me. So I've got 100 meters by 60 meters. And a path of constant width, so it's not varying in its width, is going to be paved around the perimeter. So it's going to look like this. Inside the park, all the way around the outside of the park, is going to be a path with a width of x, and that's going to be all the way along. This is x. Here to here is width of x, and here to here is a width of x. And the mayor wants to be sure that the path does not reduce the area of grass by more than 10%. Obviously, some of the grass is going to be taken away, but not more than 10% of the area. So we want to find out what is the maximum allowable width of the path rounded to the nearest tenth of a meter. So we've already kind of said, okay, it's going to have a width of x. So we've already introduced a variable in our diagram. So let's make a note of that. Let x represent the width of the path. Let x represent the width of the path. So now we want to think about the dimensions of the park. And we'll write an equation to represent the area of the park. So the dimensions of the park inside the path of the grassy area that's left over, talking about this green area. I know you can't see the green marker super well, so I'll use a different color to write it, but the area of this is now has a length of 100 minus 2 times x, the width of the path twice. And the depth of the park is 60 minus 2 times the width of the path. This is now a formula that gives us the area of the grass. So this is the area of the grass. And this is after the path has been installed. Okay? Now we have the original area. I'm going to go with A sub O for original area, and that's just 100 times 60, or 6,000 meters squared. Well, what is the mayor's concern? He wants the minimum that we're allowed to go would be reducing it by 10%. So we want to find 10% of the original area, okay? So 10%, or really we want to find 90% of the original area, because that's what the minimum new area can be. So the minimum AG, that's what we've used to represent our new area, is 90% of 6,000 meters squared. So we put that in our calculator, and we get 0.9 times 6,000, which means that we're going to be left, we have to have at least 5,400 square meters of grass remaining. Okay, so let's take our formula for AG here that we just created, and we're going to set it equal to 5,400, because that's the minimum area that the grass can be. So we're going to be finding, if we're finding the minimum area that's allowed, we'll be finding the maximum x. So we'll be finding the widest that the path is allowed to be, because remember, as the path gets wider, this area of grass is going to get smaller. So we're finding the maximum width of the path according to the minimum allowable area of the grass area. So here we go, 100 minus 2x times 60 minus 2x equals 5,400. So all I've done is taken our equation for the area of the grass and said that the area of the grass, what is x going to be, so that the area of the grass is 5,400 meters squared. Okay? Well, we know that if I wanted to solve this, I need to have it in standard form, and I have to have it set to 0. I don't have that right now, so I need to get 5,400 on the other side and 0 on the right. And in order to actually combine all my like terms, I have to FOIL this thing out. I have to distribute the left side here and expand it. So I'm actually going to be doing first times first, outside times outside, inside times inside, last times last. And once I have that all regrouped, I'm going to subtract 5,400 from both sides. Okay? So if we're taking that note, we're saying expand left side. So 100 times 60, 6,000. 100 times negative 2x, negative 200x. Inside times inside, negative 2x times 60 is negative 120x. Negative 2x times negative 2x is positive 4x squared. On the right side, I still have 5,400. I'm going to group like terms and rearrange in descending powers of x. That step is called simplify. So I'm going to take what I have here and simplify. You can see I have only one x squared term. It's 4x squared. I have two terms with x. They're both negative. I've got negative 320x. And I have positive 6,000 as the constant. And on the right hand side, still 4,500. Alright. Next step. Write in the form ax squared plus bx plus c equals 0, which means I'm going to be subtracting 5,400 from both sides. Leaves me with 4x squared minus 320x plus 600 equals 0. Well, from here, I know that I want to be finding the value of x that will make this equal 0. That's called solving the equation, and that's going to give us the width of our path. So I'm just going to apply the strategies that I use for factoring. It's big numbers. I could do sum and product. I could try and see what I would get. But I noticed something first. They're all even numbers. And actually each of A, B, and C are divisible by 4. So instead of, there's two different ways you can think about this. We've been pulling out a greatest common factor. So I could pull out that greatest common factor from each term and write the 4 out front. That would be fine. But I notice I have a 0 over here. So what I can actually do is divide every term by 4. It's essentially the same thing as pulling it out, factoring it out of this side, and then dividing both sides by 4. 0 divided by 4 is still just 0. So it's not going to affect the right side at all. But here we go. I'm going to simplify by dividing by 4. So technically I'm dividing both sides by 4, but it's not going to change the right side at all. Over here, 4x squared divided by 4 leaves me with x squared. 320 divided by x, 320x divided by 4. 320 divided by 4 is 80, so I have 80x. And 600 divided by 4 is 150. Now I could be looking for two numbers that multiply to 150, add to negative 80. I would go through my list of factors of 150, and I would figure out that none of them add to negative 80, which means I need to use quadratic formula. I'm going to some room off to the side. I'm going to just erase what I have here and do my quadratic formula work off to the side here. So we've got x equals negative b plus or minus the square root of b squared minus 4ac over 2a over 2a. And now I just plug in what I know. B is negative 80, so I'm going to be having a negative 80. Well, a negative and a negative is a positive. Negative times negative is a positive, so I'm actually going to have just 80 on the outside here. Plus or minus square root of negative 80 squared. Notice I put that negative 80 in brackets because I want to make sure I remember to square the negative sign with the 80. This is going to end up being a positive number. Minus 4 times 1, which is A, times C, which is 150, over 2A. And I'm going to work this out inside my square root here. In order to do this, I just do 8 squared and add 2 zeros, right? So I've got 6,400 minus 600. It's 150 times 4 over 2. One more step before I get my calculator out. 6,400 minus 600 leaves me with 5,800 under the radical sign. That over 2. It's going to give me two solutions in my calculator. I'm going to do 80 plus this divided by 2, and then I'm going to do 80 minus this divided by 2. And what we end up getting as our results, as our solutions for x is approximately 78.1, or x is approximately 1.9. So it appears as though there are two possible widths for our path. The first width, the path could be 78 meters wide, or the path could be 1.9 meters wide. Well, if we wanted to double check, we could put each of these answers into our dimensions up here. And what would we find out? Well, let's just round this to 80 and chuck it in here just so I can show you. You'd have 100 minus 160. That's a negative dimension. That doesn't make any sense. Same thing happens over here. 60 minus 160. Okay? You don't have a positive dimension there, so that's impossible. Okay? Which leaves us with the path having a maximum width of 1.9 meters. And we could find out what the dimensions would be if the path was 1.9 meters wide. You would have one dimension of 100 minus 2 times 1.9, which is 100 minus 3.8, which is 96.2 meters. And the other dimension would be 60 minus 2 times 1.9, which is 60 minus 3.8, which is 56.2 meters. And again, we could double check that the area that we have is equal to or greater than the allowable area of 5,400 meters squared. We would just go 96.2 times 56.2 and punch that into our calculator. We would get 5,406.44 meters squared. So that falls within the allowable area for the grass area, according to the mayor. So he's going to issue the decree that the path should be 1.9 meters in width. Again, running through it so we can remember what we were doing. I started with a diagram of the park, 100 by 60. We kind of arbitrarily drew this grass area to show that the path had a width of x all the way around. So that's going to be reduce the width by 2x, and it's going to reduce the depth by 2x. So the new dimensions are 100 minus 2x and 60 minus 2x. We found out what 90% of the current area was, 5,400, and we found out what width of the path, what value of x would allow us to still have an area of at least 5,400. And we found out that that path width through using quadratic equation was 1.9, quadratic formula, sorry. Example 3 deals with consecutive numbers. We're going to need to find two numbers that do something. These are some of my favorite problems. They get you thinking a little bit about numbers and how they relate to each other, coming up with variables and the equations needed in order to solve things. So we're told that the product, keyword, of two consecutive even numbers is 5,624, and the question simply is, what are these numbers? Well, what do we know? Consecutive means right beside each other, but they're even. So this means even numbers that are right beside each other. So our options, if don't write this, but if I'm looking at my number line, I could keep on going, yada, 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 9, 10, 11. 2 and 4 are consecutive even numbers. 4 and 6 are consecutive even numbers. 2 and 6 are not consecutive even numbers. Okay? So we're looking for something like 8 and 10 could be the two numbers if the product of 8 and 10 was 5,624. It's not, it's 80, so we know it's not, and we know we're looking for bigger numbers. Okay, well, let's let x be the smaller number. Well, what's my other number going to be if it's a consecutive even number? Well, just to the consecutive number, I would use x plus 1, right? If I needed to go from 4 to 5, I'd do x and x plus 1. But I need another even number, so I actually need x plus 2. Okay? Let x be the smaller number, and x plus 2 be the other number. And I don't actually really care which one is smaller. I shouldn't have said that. I should just say let x be one number and x plus 2 be the other number. Now we need to write and solve an equation to find x. Well, what do we know about x and x plus 2? we know that x times x plus 2 is 5,624. This is pretty straightforward. From here, it's pretty simple quadratic. But again, it's not in standard form. So what do we need to do? We need to expand the left side and then put it in standard form, which would make it equal 0, okay? So here we go. We're going to expand the left side, then write as ax squared plus bx plus c equals 0. So expand the left side. X times x is x squared. X plus x times 2 is 2x. And I'm right away going to do the next step as well. I'm going to subtract 5624 from both sides. Now in order to factor this, I'm looking for two numbers that will multiply to negative 5,624 and add to positive 2. So if I'm looking at sum and product, I've got a product of negative 5,624 and a sum of 2. This negative sign tells me that out of the two numbers, one is going to be positive, one is going to be negative. The fact that they add to positive 2 tells me that the larger number is going to be positive and the smaller number is going to be negative. So I'll just go through my list of factors, listing them all. 5,624 times 1, split it in half, you can divide it by 2. Okay, it's not divisible by 3. You can go down the whole list, guess and check. You could also use your calculator to try some guesses. I'm going to take 74 and 76. 74 times 76 is 5,624. To decide which one is positive and which one is negative, I look over here. 74 is negative because negative 74 plus 76 is 2. So I can move back over to my work here. What did that tell me? Well, I've got my two binomials being multiplied by each other. The second term in the first binomial is negative 74. Second term in the next binomial is positive 76. Which gives me, actually, my two solutions. So this tells me that either, for this statement to be true, either x minus 74 equals 0, or x plus 76 equals 0. Let's work over here in the first case. Add 74 to both sides, x equals 74. Over here, subtract 76 from both sides, x equals negative 76. Now, you're looking at these two numbers and you're saying, well, they're not actually two apart, are they? We needed consecutive even numbers. These guys are not consecutive. They're actually way on opposite ends. These don't actually go together to solve the problem. They are two different possible solutions just for x. Well, what did we say about x? We said let x be, I'm just going to call it an even number, which means that this x actually goes with a different x plus 2, and this x has to go with its own x plus 2. So let's find the buddy that goes with each of these solutions. If x is 74, then x plus 2 is 76. And over here, if x is negative 76, then x plus 2, I have to add 2 here, going closer to 0, it's going to be negative 74. Well, now let's think if we can see what we just did and see if we can make the connection here. Let's see if this is true. That now I'm saying this is a pair that satisfies the problem, and this is a pair of integers that satisfy the problem. That would mean that these need to be both even integers and they need to be consecutive. 74, 76. Yep. Do they multiply back to 5,624? Yes. So this solution is good. But let's look over here. is this another option? Yeah, they're negative numbers, but they're still even numbers, and they're still consecutive. If I'm counting, I get from negative 76, the next consecutive even number is negative 74. So let's see if they multiply to our product. Well, you can see they're going to. It's the same numbers as up here, and two negatives make a positive. So they do also multiply back to 5,624. So what we're figuring out here is there are actually two solutions for this, just like there always are in a quadratic situation. The numbers are 74 and 76, or negative 76 and negative 74. All right, two options there. Example 4, we're going to be applying our skills using quadratics and solving quadratic equations, dealing with a right triangle. So we have one leg of a right triangle is 1 centimeter longer than the other leg. So in order to get my bearings here, I'm just going to draw a right triangle, and I'm going to try and make it look like one leg is 1 centimeter longer than the other leg. Okay? Well, without reading anymore, I can still introduce my variable. I'm going to let x be the shorter leg. Okay? So over here we have x, which makes this leg x plus 1. Let x plus 1 be the longer leg. Why? Well, because it's 1 centimeter longer than the shorter leg. Get out my trusty ruler, draw my hypotenuse, and the length of the hypotenuse is 9 centimeters greater than that of the shorter leg. Let x plus 9 be the height. X plus 9. Find the lengths of the three sides. Do I have any tools in my toolbox that relate the three sides of a right angle triangle? I do. Pythagorean Theorem. Pythagorean Theorem says a squared plus b squared, the two legs, is equal to c squared. So let's plug in what we know. A is x, so one of my legs is x, and Pythagorean Theorem says take x squared. And I'm going to add my other leg, which is x plus 1, square it. It's going to be equal to c, which is the hypotenuse, which is x plus 9, and I have to square that. Okay, common mistake would be to write this something like this. X squared plus 1 equals x squared plus 9, or even x squared plus 81. That would be just as wrong. Okay, it's not what we have. We have the length of the side, which is x plus 9, and that whole length is squared. Same thing here. The length of the side is x plus 1. That whole length is squared. I need all this information multiplied by itself again. Okay? So let's go ahead and simplify this. We're using BEDMAS. We're going to expand this out. We're going to group like terms. We're going to get it in this form. ax squared plus bx plus c equals 0. And then we're going to solve it. If you'd like to try this one on your own and then check back, go ahead and pause the video. I'm going to keep going. X squared doesn't change. I'm going to use my patterns from lesson 5.2, I believe. A squared plus 2ab plus b squared. So this guy expands to x squared plus 2x plus 1. And same pattern here. X squared plus 18x plus 81. Now I'm going to group my like terms. I'm going to move all these guys over by subtracting x squared from both sides, by subtracting 18x from both sides, and by subtracting 81 from both sides. And that's going to leave me with 1x squared minus 16x minus 80 equals 0. Okay, so we've gotten it into the right form, set it equal to 0, and now I can factor this. I'm going to use sum and product. I'm looking for two numbers that multiply to negative 80 and add to 16. I know 20 times 4 is 80. One of them has to be negative. The bigger one is going to be negative because I'm left with a negative here. So I know that my two numbers are going to be negative 20 and positive 4, which tells me that, I'll do the work here, x minus 20 equals 0, or x plus 4 equals 0. So the solutions, x equals 20, or x equals negative 4. So you'd think you're done here, but one of these answers, one of these solutions is not a reasonable answer, and it shouldn't take you too long to figure it out. If you're thinking about the scenario, this is the length of the side of a triangle. Well, can we have a negative length? We cannot. So we reject the root x equals negative 4. Reject the root x equals negative 4. And before we confirm anything, we're going to check x equals 20 to see if that actually satisfies and verify that it is a right angle. So, a right triangle. So if x is 20, then x plus 1 is 21, and x plus 9 is 29. We want to find out if this is actually a right triangle by, again, using Pythagorean Theorem. So basically what we're saying is that we should be able to go 20 squared plus 21 squared on my left side should end up equaling the right side of the Pythagorean Theorem, which would be the hypotenuse squared. Alright, here we go. 20 squared is 400. 21 squared is 441 for a grand total of 841. And over here, 29 squared, chuck it in your calculator, is 841. So the left side equals the right side, and this is a good solution. X equals 20 is a good solution for this right angle triangle. So the three sides of the right angle triangle, that was the goal of the problem. Therefore, the three sides of the triangle are 20, it's all in centimeters, 20 centimeters, 21 centimeters, and 29 centimeters. Alright, your practice problems are listed for you at the bottom. They come from the worksheet on the next page. 1 through 6, 8, 10, 11, 13, and 18 come to class with questions ready to work hard. Okay, as we move into solving word problems using these methods, we're going to talk about some strategies. We're going to follow these particular steps when determining an algebraic solution. So the first one is you want to define your variables. So remember, we're going to be reading word problems. We're going to be converting words into algebra. In order to do that, we need to define our variables. That's let a equal this, let b equal this, or let x equal this, or x represent this, and y represent this. Okay? Define your variables. Then you are going to write an equation to model the situation. Then, well, we're not quite at solving. If you can, you want to simplify it. So do whatever you can to simplify first. Then you're going to try to solve. What does it mean to solve?
Plug x where it is, and plug y where it is.
Yep. Find out the value of x, right? Find out the value of the variable that you chose. Okay, so you're going to solve the equation using an appropriate method. And those are the 4 methods we talked about earlier.
How do you know when you have to use the completing the square?
You use your brain.
We'll get there.
Okay, cool.
When do you, well, completing the square puts it in vertex form. So if you're finding the maximum of something or the minimum of something, that's the key that you're looking for vertex form.
And you have the.
Okay? If you're looking for where the ball hits the ground, that's a key that you're looking for factored form, x-intercepts. Okay?
Yeah.
Step 5, you are going to consider any consider any solutions that are not allowable. Consider any solutions that are not allowable.
Is that a word? Allowable?
And then provide appropriate reason.
Is allowable a word?
Yes.
Just wrote it, so.
It's a word.
Well, not necessarily.
What does that mean? Well, that means if I am looking for the places where the cannonball that got shot out of a cannon, where it hits the ground, this is not an allowable solution because the cannon probably got shot from right here. Okay, so this solution doesn't even make sense. It would be going back in time. There's only one solution for where the cannonball hits the ground. It's right here. Okay, even though if I use the equation and draw the parabola, I can get 2 things. And last thing, concluding statement. Provide a
Appropriate answer.
concluding statement.
You literally just.
Okay, we're on example 1, page 22 in your notebook. The formula, so this is a toy rocket. It's being shot up in the air, and the formula is given to us there. It's -1/2 g t squared plus velocity naught, so that's the starting velocity, times t,
Velocity not.
plus h naught. So that subscript 0 is naught. It's just, it means that's where it's starting from. So it's the velocity at the very beginning when it gets shot, and it's the height at the very beginning when it gets shot. Okay? Excellent. Can be used to model the height of the projectile, where g is acceleration due to gravity, so that's the force that gravity is pulling on something, which is 9.8 meters per second squared on Earth. Velocity, v naught, v sub 0, is the initial vertical velocity in meters per second, so it's only considering the upward thrust of the rocket. It's not considering the horizontal. Like if it's shot out at an angle like that, we're only talking about the upward action, okay? And h sub naught, h naught is the initial height in meters. So here we go. Create a model.
Wait, would H be the where it's at its highest point for the max?
Well, height can be, so basically we're going to have something that looks like this.
Yeah, but H would be the top, right?
H is any height. It's going to be this height, this height, this height, this height, this height at certain points along its projection, right? So h and time, that's the relationship here. Over time, it will go up and then it will come back down. Okay, so h could be anything. It depends on what t is. That's why t is the independent variable, h is the dependent variable. Okay, the equation is h in terms of t. So in A, we are to create a model for the height of a toy rocket. Create a model just means write the equation. It can be modeled by an equation of a toy rocket that has these specific qualities or attributes or characteristics. It is going upward at 60 meters per second from the top of a 3-meter platform. Okay, so we already said that to model it means I'm just going to take my equation, -1/2 times g times t squared plus v naught times t plus h naught.
So do we have to actually know knots now?
Like tying a knot?
No.
It just means the starting velocity, the initial velocity. It was right there in the question. Okay? And we already know from the scenario, what's g represent?
Acceleration.
Acceleration due to gravity, which is What's the value of it?
9.8.
It's 9.8 meters per second squared. Okay, so G 9.8 is going to go in our equation. Now, in A, we are told the initial velocity. What is it? The vertical velocity.
Oh.
Velocity known.
60s.
60. Good. 60 meters per second.
3.
And the initial height is 3 meters.
Is not sure what they talk
Oh.
about flying.
So now all I have to do, different. All I have to do is plug in the things that I know for my variables. So they have defined the variables for us already.
Wait, that's an
Now what
H,
we're
right?
going to do is we're going to sub these things in. So we've got h is equal to -1/2, and here's where I'm going to sub in g, which is 9.8, and I'm going to sub in t. Oh no, I don't know t, so it's still just t squared.
That's what we're
I'm going to
finding.
add velocity times t, which is 60 times t, and I have the initial height of 3. Now some things
It
you...
looks like a quadratic expression.
No, it's
It
not.
is a quadratic expression. Good. Okay.
What else?
We can reduce this further. Okay, right here I just have multiplication. I've got -1/2 times 9.8, so I just need half of 9.8, which is 4.9, and I have a negative times a positive. So here we reduce, we simplify to 4.9 t squared plus 60t plus 3. Now some things I already know about this. It's in standard form. It's now going to model the path of the rocket. I know that this is, look, its initial height just went right there. See that? Initial height of 3 meters. What does that tell me? Well, that actually tells me that the y-intercept is 3.
Oh, so where they land, where they started
That's why you
off.
didn't have
that
to
means all
think
of-
at all on your quiz. Because it's literally right there. Y-intercept. Okay?
We all have our test back, but like, it's okay.
All right, we have our equation to model this projection of the toy rocket, and now we're looking at B, and B says, how long would the rocket take to fall to Earth, rounded to the nearest hundredth of a second? So, here's where it hits Earth, according to our little sketch. What am I looking for? What is the goal of this situation?
To find the time. To find t.
T, when?
It hits the ground when y is 0.
When, excellent. When h is 0, I want to find out what t is when h is 0. That is great. So look at what we're going to do. We want to find t when h is 0. So sub h equals 0. And solve for t. Okay? So here we go. We've got h equals 0. So 0 equals -4.9 t squared plus 60t plus 3. Now we want to solve for t. So what strategy am I going to use?
Division.
Track 3 first. Algebra.
I want to factor it. Excellent.
Wait, can
Now,
we use,
I'm
can
looking
we
at
use
this,
squaring?
and I'm seeing you can use complete the square. Yes. We're not going to. Look at this. I cannot factor this easily. Look, I got a -4.9 times 3 for my product. So then I'm going to use my quadratic formula. Okay? So here we go. Paying attention. Who's got the song for us?
Negative B, negative
We saw
B.
it.
Plus or minus, plus or minus,
Negative B.
Squared minus 4ac.
square root.
Square root of
B
b
squared minus 4ac over a. That 2a over 2a.
Not bad. Okay.
No, I did it
So here we go. Sub in what we know. We have all of the ABCs. I can write them here to help myself out if I want to. I've got A equals -4.9, B equals 60, C equals 3. So here we go. X equals -b, -60, plus or minus square root of b squared. That's going to be 60 squared minus 4 times -4.9 times 3. All over 2 times -4.9. Okay? Let's work this thing out. X equals, I'm going to leave this -60 out there for now.
Can we just do it as like a class?
No, we're going to
Sure, go ahead and try it and then check back in. If you're trying it on your own, go ahead and check the board to see if you have the same next step as me. And I'm actually just going to continue it on out from here. There's only one more step before I use my calculator. So my next step is x equals negative 60 plus or minus, and I can put these numbers together. 3600 plus 58.8 is 3658. Nope.
Yes.
No, it's not.
Nope.
Yep.
No, because you get two
Two
positives.
subtractions equals positive.
Over negative 9.8. And from this point, I'm going to just put them in my calculator. My one solution will be negative 60 plus this square root of 3658.8 divided by negative 9.8, and my other solution will be negative 60 minus that. So we check this in our calculator, and we end up with t equals, I've been using x all along in my notes, but should be
So,
looking for
say
t,
if you're using x and y, would that be x or y?
x. So t equals negative 0.05, or t equals approximately 12.29. Even if you're still trying to do it on your own, please just stop and let's pay attention here. What do these solutions tell me? The goal was to find out where this toy rocket is going to hit the
You
ground.
can't go negative.
Yeah.
So we can look back and we can say, well, it's not going to be, we're going to reject this answer because you can't go back in time from shooting a rocket, and if you did, it would just be still on its stand. So that's not a useful solution. What does this tell us?
That it 12.29 equals 2.
So at 12.29 seconds,
It will be
This
at 3 meters.
this toy rocket is going to hit the ground. It's going to be at 0.
Start at-
That's why we started this whole thing with h equals 0.
Wait, t is time?
T is time, the time it takes for the rocket to hit the ground, 12.29 seconds. And I want to add that as my closing statement. It would take about 12.29 seconds
But why about? Wouldn't it be exactly 12?
to hit
Because we're graphing, it's never exact.
the ground. Well, we didn't solve by graphing, but I have this. The square root of this is, we rounded it to 2 decimal places. Okay, it's approximate answer.
Oh, but we
is it-
graphed that information, didn't we?
Is it more like
C, have a look at C, please. It says, what is the maximum height of the rocket rounded to the nearest meter? So on our sketch now, we're looking for the maximum height. Now you could do this a couple different ways. You can find the vertex by completing the square. Don't do that. Way too much work. Okay? You could take the average of your x-intercepts in order to find the axis of symmetry, and then find out what h is at that value of x, of that value of t. Don't do that. Okay? Too much work. That's probably what I would do, though, because I would forget this formula. We do have a special formula that helps us find the x-coordinate of the vertex. So I'm going to write it, this is actually th, right? T being the horizontal coordinate, h being the vertical coordinate. So we can actually find the t coordinate of the vertex.
Didn't we have a formula saying like we could just divide them? Or,
The
like,
t coordinate
Find the average, yeah.
of the vertex. Yep, you could find the average of the two. The t coordinate of the vertex is t equals negative b over 2a. If you've never seen that before, that's okay. It's just a formula that you can use if you can remember it. So what this tells us is that that t coordinate is negative, and then in the numerator b, which was 60, and then in the denominator 2a, which is 2 times negative 4.9. Throw that in my calculator. I end up with a negative over a negative, so the answer is going to be positive. I end up with 6.12 seconds. So that tells me that we're going to reach our max value at a time of 6.12 seconds. Now, does that give me the maximum height? No, it gives me when the maximum height happens.
So now we have to see how fast it traveled in 1 second.
Was that when we sub it into the equation?
So in order to find the height at that time, all I have to do is take my equation, which was simplified to negative 4.9 t squared plus 60 t plus 3. And everywhere I see a t, I'm going to sub in this time that I found, 6.12. And I'm going to remember to put it in brackets and square it because t is squared. And in the second term, t is not squared. So I just have 6.12 times 60. And I'm going to add 3 at the end. So you can punch that in your calculator. You will end up with an approximate height of 187 meters. So this rocket reaches a maximum height of 187 meters at 6.12 seconds.
In 6 seconds.
That's insane.
Okay, the last question is a little bit tougher. I'm going to erase what I have here. And the last question says, okay, when, that's great, we know the max height, we know how long it's in the air, we know when it hits the ground, but what I want to know is, for how long is it higher than 150 meters? Okay, so we want to find out the time interval from here to here.
Wait, why? What? Sorry, you drew the line
Yep,
at 50 meters.
at 150 meters.
Could you, okay, could you like switch the so you can see the line?
Okay. So we're looking at what time interval is it higher than 150 meters? Well, it's really the exact same question as find the x-intercepts, except now I'm not setting h equals 0, I'm setting h equals 150. Okay? So it's the same question as finding the x-intercepts. I'm still going to factor or use quadratic equation, quadratic formula. But now I'm not setting h equal to 0, I'm setting h equal to 150 meters high. Okay? So here we go. Now we have, let h be or equal 150. So, negative 4.9 t squared plus 60t plus 3 equals 150. We're going to find the two spots where it hits. We're going to find out where it equals 150, and then we'll be able to say, oh, it's above 150 meters in between those two positions. Right? This whole part, it's clearly above 150 meters.
But
So that's what we're finding.
Since we know t, would we just
This is now not in standard form. So in order to solve this, in order to either factor it or use quadratic formula, I need to have it equal to 0. Well, how do I do something fair? Rearrange this so that I have 0 on the right and all my other stuff on the left.
Minus 150.
I'm going to subtract 150 from both sides. Okay? So I'm going to have negative 4.9 t squared plus 60t minus 147 equals 0. And now again, this is too hard to factor, so I'm going to use my quadratic equation. I'm not going to rewrite it this time, I'm just going to sub my points in, and after I sub the points in, I'm not even going to solve it, I'm just going to give you the answer. But if we subbed our points in, we'd have negative b, it's negative 60, plus or minus the square root of b squared, which is 60 squared, minus 4a, which is negative 4.9, c, which is negative 147. All over 2a, which is negative 4.9. Okay, so again, you would go through this step by step. You would do 60 squared, which is 3600. You do negative 4 times negative 4.9 times negative 147, which gives you a big negative number here. Okay, but I know it won't be as big as this number.
Well, I thought you couldn't have a negative number over.
It won't be. Once this whole thing under the radical will not be a negative number. This portion of it will be, but you still have to add 3600. Okay? Good. If you do the math on this correctly, you will end up with the solutions, and again we're finding t. you will end up with the solutions. T is approximately 3.39 seconds, and T is approximately 8.86 seconds.
So could we find those?
So what did we just find? Well, we found where the rocket cracks 150 meters on the way up, 3.39 seconds, and we found where it crosses back down past the 150 meter marker at 8.8 seconds. So what is the interval? It's therefore the height of the toy rocket is greater than 150 meters between 3.39 seconds and 8.86 seconds. All right, I will finish this video after school, and you will watch the rest of it on YouTube.